couple of comments on some work I handed back in Friday's lab. Okay, we have a situation where one car, I believe, is moving south, another car moving west, and they collide and stick together and move off in some specified direction. Okay, we're given the initial speed of each car. To set that problem up, we simply set the total momentum, which is known before collision. I think we had a 1,500 kilogram car. Actually, it wasn't known. We didn't know the two velocities beforehand. Sorry, I was wrong about that. I didn't really look at this before I started talking. I probably should have. Anyhow, we have a 1,500 kilogram car at some unknown velocity in the negative J direction. That's the car moving west. And the car moving south is moving in the negative I direction. It's 2,000 kilograms, some unknown velocity, which we'll call V2. And then afterwards, we're given the velocity, the speed, and direction of the cars. It's at 30 degrees south of west, which is 210 degrees on a standard coordinate system. And we were given the speed of the car. We have a total of 3,500 kilograms, and I suppose then it must be moving at like 2.1 meters per second or something like that to get this magnitude of the momentum. So the bottom line is, though, when we set this up, we don't scramble around. I think it's better not to scramble around setting up X equations and setting up Y equations and treating it all as two separate cases, although it sort of is. It's a little more elegant to set it up as a simple equation involving vectors. So our momentum here, we have an I component and a J component. Our momentum here, we have an I component and a J component. Very easy to write. And we set these two equal. Right here is our equation. And of course it does break into an equation where the I components are equal and the J components are equal. More elegant to write the equation out like this, though, than to write separate cases. Not wrong to do that, but more concise. Okay, another problem. We have a stationary mass and another mass hits it, and they stick together and move off at some velocity. Okay, and the masses turn out to be equal. Right now I'm writing them as separate. So before collision, one mass is stationary, has no momentum, the other mass has some velocity. And after collision, both masses move off together with the same velocity. Now, and this is a collision in one dimension. If the two masses are equal, then it turns out that we have mass 1 times V1 and essentially double whatever the common mass is times V1 and twice that mass times U, so that U is 1/2 of your initial velocity of the first ball. So what does this say about the kinetic energy of the system? Well, the kinetic energies beforehand is 1/2 the mass of one ball, and I think I've got an error here. Let me correct this. Okay, I missed the fact that you have twice the mass here and only the mass here in what you saw previously. So that the ratio of the kinetic energies is, well, I've gone ahead and written everything out. It's 1/2 times the 2m times u squared over 1/2 times m times your original v1 squared. And then the 1/2s go away. We have 2m over m. Of course, that could just be written as 2, but reminding ourselves of where the proportionality comes from. Twice the mass here contributing to this kinetic energy, only one mass here contributing to this kinetic energy. And then that's multiplied by the ratio of the squared velocities, u squared over v1 squared. Since u is 1/2 v1, u squared is the quantity 1/2 v1 squared, which is 1/4 v1 squared. We divide that by v1 squared. So from the mass ratio we get 2, from the velocity ratio we get 1/4, giving us a ratio of 1/2. So here's our mass ratio, here's the ratio of our squared velocity, and here's our kinetic energy ratio. Now my point here was that you could very quickly do some simple ratios, some simple proportionality, but again, I made the error in trying to make this point of only using the proportionality of the velocities, and the squared velocities would have a proportionality of 1/4. The velocity after would be, the squared velocity afterwards would be 1/4 the squared velocity of the first object. But again, mass ratio also has to come in, so I kind of short-circuited it while trying to make the point that proportionality reasoning can short-circuit the whole reasoning process, or can speed up the reasoning process, can take us right to the heart of the process. And that is true as long as we remember to use all the relevant proportionalities. Now, in another example, we have a hanging ball hit by a dart which sticks in it, takes the ball up to the top of a circle. You want the ball to complete a whole circle. Now, if the ball is going to complete a whole circle, then at the top, it has to have, well, at the top, the acceleration of gravity has to equal or exceed the centripetal acceleration that you would have at the top, so that the centripetal acceleration has to be at least v squared over r equal g. So velocity at the top has to be, velocity at top squared over r has to be greater than or equal to g. Now we're looking for the minimum velocity, so we're just going to set it equal to g, and we get the, let's say, the kinetic energy at the top. Not sure why I said kinetic energy, but that would be the velocity at the top. Okay, the velocity at the top would be the square root of rg. And then when you get the kinetic energy at the top, of course, it would be 1/2 mv squared, so it would be 1/2 rg. And there are more questions in the problem, but the one error people were making where they were just getting the ball up to the top, not giving it enough velocity at the top to maintain its circle.